Hello everyone, welcome to Latent Code. In the previous video we saw why the naive implementation of SPSC queue fails. In this video, we'll try to fix it using Mutex-Based. Not because they are fast or performative, but because it sets a correctness baseline. So let's dive in. Before that, we need to understand what mutex are. A mutex is a synchronization primitive that enforces mutual exclusion. You can imagine it as a lock that guarantees that only one thread at a time can execute a protected section of the code. In a sense, no other thread can access the same portion. So it has the exclusivity and lock over that critical section area. Alright, now that we have understanding of mutex, let's dive in and fix the naive SPSC queue. We start with two threads, a producer and a consumer. The producer wants to enter the critical section, it calls lock. Now look at the central panel. This isn't a simple variable assignment. The hardware prepares an atomic compare and swap. Under the hood, Mutex use compare and swap operation at really low level. So it expects 0 and the actual value is 0. So it's good to go for acquiring the lock and swaps it with 1. So now the mutex state is 1. It's locked. Now the consumer calls lock, but what happens? It does the CAS comparison again and it expects 0, but it actually got 1. It means that the mutex is already locked, so the consumer can't acquire the lock, so it fails. Now in a bad implementation, the consumer would spin in a loop, burning 100% of your CPU. But mutex is smarter. Since the lock is taken, the C++ runtime makes a syscall. It tells the OS, put me to sleep until this address changes. The consumer is not blocked, saving your battery life. Eventually the producer finishes the execution and it calls mutex unlock. This does two things. First, it sets the atomic flag back to 0. Now the mutex state is 0. It's unlocked. It signals the OS scheduler to wake up any threads sleeping on this address. This wakes up the consumer. It retries that cache operation, finds that the value is 0 it was looking for, swaps it 1, and finally enters the critical section. This is the happy life cycle of a lock. But there is a massive problem. Look closely at the producer. We manually called lock unlock. What happens if we return early? What if code throws some exception? We skip the unlock. The consumer stays blocked forever. This is how you get deadlock. This is why in modern C++ we almost never call lock and unlock manually. We use RAI, that is resource acquisition is initialization. We wrap the mutex in a std lock guard. It generates a constructor that locks mutex immediately and destructs it when its scope ends. So you don't have to manually lock and unlock, it does it automatically for you. It makes your code cleaner, safer, and deadlock resistant. So remember, under the hood, it's atomic hardware instructions. Now let's dive into the code. In the last video, we saw the exact implementation of naive SPSC queue. In this video, we'll be fixing it using a queue to establish correctness. We add mutex to the queue and guard all the shared data, the head, the tail. Every enqueue and dequeue operation acquires the lock before touching shared data. So here we have defined the mutex and we'll be using lock guard as discussed already, that it's constructed and destructs automatically when it goes out of scope. This makes the code exception safe and prevents common locking mistakes. In enqueuing, we acquire the lock, check whether the queue is full, write the data, and advance the tail. While the lock is held, the consumer cannot observe any intermediate state. Similarly, in the dequeue, we acquire the lock again. Before checking if the queue is empty, read the data and advance the head. Because both sides uses the same mutex, there are no data races. This implementation of mutex gives us two guarantees. Mutual exclusion happens before relationship. When the producer releases the lock, all of the data it writes become visible to the consumer when it acquires the lock. That's the key difference from the naive version. Now let's start executing and see the result. I've already compiled it and you can see that there are 0 lost values and 0 duplicate values, and we have achieved the correctness we were looking for. Just to make sure, it didn't happen by chance, we'll execute it again. You have noticed that it takes longer to execute the mutex code. It's because acquiring lock and releasing the locks takes time, and also it adds extra synchronization overhead. So it's a bit slower than the naive implementation. On the other hand, if I execute the naive implementation of the code, you can see it's faster, and we also see that there are data races and duplicate values, lost values. So finally we have achieved what we were looking for, the correctness. Though it's not that performative, it's a bit slow, but the correctness is all that matters, and we have achieved this. In the next video, we'll make this code performative and faster using the automix. Thank you, stay tuned and subscribe.